Most mornings start the exact same way. You look at your phone, check a weather app, and try to figure out if you need a heavy coat or a light jacket for the day. When you look at those forecasts, they rarely give you a single temperature. Instead, the most prominent numbers on the screen are a high and a low. That dual number system is completely different from how we measure our own health. Looking at this clinical thermometer, you can see the scale is incredibly narrow. It only runs from 35 to 42 degrees Celsius. A healthy human body tightly regulates its internal heat, rarely drifting more than a fraction of a degree from normal. The air outside lacks that regulation. The atmosphere is highly volatile, dropping to a bitter chill before dawn and then climbing to sweltering heat by mid-afternoon. Because the heat of the atmosphere is never static, knowing the temperature at 8 a.m. tells you almost nothing about what you will experience at 3 p.m. To accurately track weather patterns, meteorologists have to identify the absolute boundaries of that daily swing, the peak heat and the deepest cold within a 24-hour cycle. Finding those exact numbers presents a major physical problem. A human observer cannot sit perfectly still, staring at a glass tube for 24 hours straight, just waiting to catch the highest and lowest readings. Scientists needed to invent a specialized tool capable of automatically trapping the high and low points of this daily thermal roller coaster without requiring a human to watch it happen. Standard instruments fail at this task. This is a typical laboratory thermometer, built with a long, straight glass tube and a single column of liquid. Its primary function is to measure immediate, real-time environments. It tells you the exact heat of a substance at the specific second you look at the scale. If the temperature rapidly spikes and then drops back down while no one is in the room, that data is gone. Without an observer present, the extreme high point is completely lost from the record. To solve the observation problem, meteorologists use the maximum and minimum thermometer. Unlike standard models, this device relies on a distinct U-shaped glass tube. Inside the U-tube, expanding liquid responds to rising heat, pushing upward and driving a metal marker. As air cools, liquid retreats, leaving the marker suspended at the absolute highest point. The exact reverse process traps a second marker at the coldest point. The gap between those two locked markers is formally known as the temperature range. Finding this range requires a simple calculation. You just subtract the minimum from the maximum recorded number. This specific piece of data helps local communities prepare. A wide temperature range tells farmers a mild afternoon might end in a crop-killing frost, while a high minimum number warns city planners to prepare for a heat wave that won't cool off after sunset. By utilizing a tool that leaves a physical footprint of the heat, we capture a permanent record of the daily extremes, skipping the impossible task of constant observation. Capturing the data is only the first step. We still have to ask what specific environmental forces are manipulating the air to create these massive swings in the first place. The primary driver is the time of day. As the Earth rotates, the changing angle of the sun dictates exactly how much direct heat energy enters the local atmosphere hour by hour. Next are local weather conditions. Cloud cover acts as a massive thermal blanket overhead, blocking incoming solar heat during the afternoon, or trapping existing heat near the ground through the night. Finally, the Earth's annual tilt and local geography permanently shift the baseline. Looking at this comparison, you can see how a high mountain peak and a flat location near the equator experience temperature ranges that sit at entirely different levels on the scale. You can conduct your own meteorological observation right outside your door to discover your local temperature range. Place a standard thermometer in a safe, shaded outdoor spot in the early morning and record the number. Then, check that exact same thermometer in the mid-afternoon. Subtract your morning low reading from your afternoon high to calculate the scale of your own local roller coaster. Tracking these numbers reveals the hidden patterns of the Earth's atmosphere, giving you the context to understand and prepare for a constantly changing environment.